Okay, good morning everyone. Let's get started with lecture number 5. As you can see, we're still waiting for the screen. Hopefully on Monday it will be here. Now, today we're going to talk about potential energy and kinetic energy and conservation of energy, and as a quick reminder of where we ended yesterday. So the work done by a force is from x1 to x2, f of x dx equals t2 minus t1. I've written it here in 1 dimensions, but it's generalizable, of course, to more dimensions. And then we defined the potential energy for conservative force such that u of x equals minus x naught to x f dx. For conservative force, please note this minus sign. If something goes wrong, it's usually a minus sign or a factor 2. And then we rewrote conservation of energy T2 plus minus integral from some kind of arbitrary reference point x0 to x2 f dx equals T1 plus, and the same from the reference point x0 to x1 f dx, and this is then our u2, and this is our u1. So we assumed conservative forces, but what is actually meant with that? So here's basically the definitions of a conservative force. So if you can write the work done from A to B as the difference of the potential energy, then you've got a conservative force. Most of the forces we're going to deal with during this term are conservative, but not all of them. We had one example with friction, where the force was proportional to the velocity, where energy is dissipated. But many of them, we really have conservative forces. There are 3 different definitions of a conservative force. They are all equivalent. Some of you may have seen that symbol that's used there. For those not, so that's nabla, called nabla, or del, depending who you talk to. And this is actually a vector. Is defined as I d by dx plus j d by dy plus k d by dz. So it's differential vector. It's used in a couple of forces. We're using it here as gradient. So the first definition here is if the force is derived from a scalar potential function along that way, you end up with a vector, and the f component in x direction is minus du by dx. The component in y direction is fy is du by dy, and so on. So the key there is expressed also in the next one. There's zero net work done by the force when moving a particle around any closed path. So that's a line integral along a closed path, and that is 0. That basically means if you move something from a point A to a point B, you can go via the straight line and get the work done. You can go like this. You can head out to Headington, come back and go here. It's all the same. It's really independent of the path you take. And if that's the case, you've got a conservative force. In vector notation, turns out to be the curl F equals 0. Just quickly gonna write that down. Again, what we've had before is that you can work that out with I, J, K. Then this is d by dx, d by dy, d by dz. And then you've got the fx component, fy component, fz component. And then you have the resulting. Just quickly, nabla is being used in a few things you will come across. So we use it as gradient in here. It's used as divergence in classical electromagnetism and a Maxwell-Faraday equation. Just for those who are interested, it will come later in that course. You can do that. And that's 0, so no sink, no source. So that's a divergence. And the other one is minus dB by dt. That's here the Maxwell equation, or Maxwell-Faraday. That will come later in another course Faraday. That's curl. So on the example sheets, you have some problems with both conservative and non-conservative force. We're going to go over some as part of this lecture. So 2 examples are shown here. We have a particle moving under a constant force in 1D. This is one of the simplest cases. Just one quick note there. If we draw that out, we have the x-axis. We have, I just would like you to correct that to V1 and not V0 there. And we have some other point x, and that little mass is being moved along this f-axis with a certain force. Now, our force in this case, Newton 2, F equals m times a, and we define and set it just out that at t equals 0, we have x equals x1 and v equals v1. That's not just our boundary conditions, which we've defined. And if we look then at T2 plus, that's a definition of it, from some kind of arbitrary point x0 to x1, f dx. F we have up there m times a, and if we write that out in T2 plus U2 equals T1 plus U1, plug that in, we get 1/2 mv2 squared minus ma x2 equals 1/2 mv1 squared minus ma x1. On both sides there is of course this term ma x0 from the integration, but that point, or the integral from this reference point, giving that's a conservative force, cancels out, and this one equals a constant. And if we can rewrite that, v2 squared equals v1 squared plus 2a x2 minus x1. So that's probably a very, very common expression most of you have seen in the one or the other form. Again, it's important to pay attention to the sign, that there's this minus sign up there. This is how the potential energy is defined. And you need to be very, very careful with that. Now, the second example is the axes are turned by 90 degrees, and we have now an acceleration due to Earth's gravity. So if we look at the potential energy at y2 and y1, and the delta is this distance in this gravitational potential, we get from y1 to y2 f y dy. This time the force is vertical along the y-axis. That's why we use the y-axis or integrate with respect to y, equals minus y1 y2 minus mgh, because it's pointing into negative direction, dy, and that's mg y2 minus y1, and I hope nobody is surprised. So this is kind of the simplest examples which we have. Let's have a look at another example, the simple harmonic oscillator. We did that during last lecture and solved the equation of motion, and it's written up there. F equals m, the second time derivative, f equals m times the second time derivative of x equals minus kx, the restorative force. The graph is shown here. You have a spring. The force is restoring it back to its to zero. We've designed the positive axis into the positive direction. Now, let's look at the two components, kinetic and potential energy, and let's start with the potential energy. Potential energy. U of x at some point x equals minus x naught to x f dx. So for potential energy, there are some conventions of where to set that x naught. Usually you set it in a way to make your life easier. We come to two examples here. The next one is on the next slide, 2 slides later, with the charges. In this example, where would you set x naught? Sorry? Exactly, where if you start the mass, it would not move. So you haven't neither displaced it either way. And that's a clever way of using it, and also setting up the coordinate system such that we go from 0 to x. Don't forget the minus kx equals kx squared over 2. So we've basically defined the 0 position such that this is where the mass oscillates about the center of oscillation. So we could have used any, but we used that one. The next one is the total kinetic energy. Kinetic energy which is of course 1/2 mv squared, 1/2 mv squared equals 1/2 mx dot squared. So the total energy, if we just add them, it's E equals Tx plus Ux equals 1/2 mx dot squared plus kx squared half. So this is the total energy of the system. We've got a conservative force. We're gonna check for the conservation of energy in there. Conservation of energy would mean conservation of energy implies that dE over dt equals 0. So the overall energy in the system doesn't change over time. Now, the equation of motion, which we had above, F equals mx double dot equals minus kx. I can rewrite that as mx double dot plus kx equals 0. That's basically equation of motion. Now, if I multiply both by x dot, I arrive at mx dot x double dot plus kx dot x equals 0. Now, if you look at this term, it is basically d by dt x dot. So it's just the, x dot squared. Chain rule for differentiation. If I do that, I end up with this term. And I can do the same on the other side, 1/2 k d by dt x squared equals 0. If I integrate that with respect to time, I end up with 1/2 mx dot squared plus 1/2 kx equals a constant. And then if I look what I have here, I've got the kinetic or the overall energy. I've written up there. And if I have a constant and I derive it with respect to time, it's not. So basically, we have we have conservation of energy. So this approach going via the energy is actually very, very powerful. You will do much, much more around that next term in Lagrangian mechanics, and will be used to solve all kinds of problems where you write down the energy of a system and then you derive the equations of motions from there. Now, we had the pendulum yet last time. I have just something quickly showing here, another quick simulation where the mass is outside. You have the potential energy at the maximum. It's all in the potential energy. And if I play that, at some point it will go into kinetic energy and around. And, well, I don't have any damping here. And you probably can imagine what happens to the total energy of the system. Oops, yeah, that's pretty fast. But the total energy of the system doesn't change at all. It stays the same. It's just fluctuating back and forth between kinetic and potential energy. Now, this is another way of representing it. Here again, this example of how the potential and the energy and the kinetic energy work together. The total energy is fixed. So we've derived that there's a maximum. And given this, there's a maximum on the extension of the spring. So the particle, or this what we have attached to the spring, can only reach locations for x that satisfy that the energy, the potential energy, is smaller than the total energy, because at that point it's maximum stretched. Here we've got all kinetic energy, and then we go back to potential energy, and it's oscillating between back and forth. So as we've seen in the example, the energy is transferred back and forth between the kinetic and the potential energy. Now, this example is slightly different, and it is something that you might come across in the prelims. A little bit more complicated. I'll tell you later what I have seen for an example in the prelims, but let's first of all solve this one. Now we have one charge fixed, so that's fixed at a position, and it has Q charge large Q. We've got the x-axis, we've got a smaller charge with small q and m. Let's just use that as, do that as q1. That's approaching with a velocity in x direction v0 on axis, so it's really a head-on collision. And we are asked to find out what is that x minimum for how far the charge can zoom there. So the forces on those charges with electrostatic forces, they are repulsive, both are positive, so they repel each other. So force on charge x force on charge q1 plus, the force is Fx equals plus q times q1 over 4 pi epsilon naught x squared in the positive direction. So the force points that way. Probably not a surprise. Both are positive. They don't like each other. Now, the potential energy at x, u of x equals minus integral from infinity to x f of x dx equals q plus over 4 pi epsilon naught x. You see here, well, in the spring, we've used the center of oscillation as reference, or as x naught, if you like. Here we used infinity because, well, if you go to infinity, the potential is 0. It's the same also being used in the gravitational potential as reference point. There, it's 0, and then you get closer to others. So potential energy equals 0 at infinity. So that's the usual convention. Of course, you can define whatever you want, but if you want to make your life more difficult, please do so. Otherwise, I think that's a nice way. So conservation of energy. Conservation of energy. The particle starts at plus infinity, so pretty far out. And that we basically have at the initial time, it has just kinetic energy. And when it gets closer at an arbitrary point, mv squared plus u of x. And if we plug that in, when does the particle reach the minimum distance? Well, at v equals 0. That's when we get the closest approach. Then that's when the particle stops and zooms away again. So for v equals 0, we get 1/2 mv0 squared equals Q1 over 4 pi epsilon naught x min. And you can rewrite that easily as x min equals Q1 over 2 pi m epsilon naught v naught squared. So we've worked out the minimum approach when for the big charge, for the red charge, when it's fixed in space. The prelim question was when the charge, the Q1, the big one, actually is not fixed. So it's actually moving around, or it can move around. Is that more difficult? Well, not really. You can use the center of mass frame. We'll come to that in one of the next lectures to solve the same example, and that was expected in the prelims question. Now, with these potentials, there are two kinds of turning points. We're looking for, if you plot the potential curve, you often get behavior like this, and you look for extrema. And there are two extrema. One is a maximum, and one is a minimum. And that has a couple of consequences, the curvature. So we know that f equals minus du by dx in the simple example. At the extrema, you don't have a force. So when you're sitting here, you don't have a force because with differentiation with respect to x is 0, and here you don't have a force. But it very much depends on what the forces are left and right of it. Whereas here at x2, when you go left, the force is pointing positive. When you go a little bit right and deviate there, the force is pointing negative. And with that, you have a restorative force that keeps it close to x2. If you do the opposite here, if you go slightly off that x1 to the right, the force will continue and accelerate it, and vice versa. If you go to the left, it will accelerate it to the left. So you basically have an unstable equilibrium when the potential is a maximum, because left and right, the force, resulting force you get by du by dx will push it off further, and this is the stable one. So the pendulum which we had, for example, or the spring, if you look at the pendulum here, it's going left and right, and you basically have a restorative force there that always, when you get off a little bit, if you go here, it's going to push it back. If you go here, it's going to push it back. The opposite is, of course, well, if you take a rigid pendulum, you have a fixed point, you start here at the bottom, and you put it up here. At the top, there's also no force, if you really put it right up. However, the second, any small fluctuations, left and right, will lead it to fall down and being an unstable position there. Now, for the rest of the lecture, a little bit more complicated examples. So what we've shown here is a potential curve in a crystal. For a single harmonic oscillator, which we've had, ux equals 1/2 k x minus x naught. If we define the x naught well, then we have it as we've used it for the example. But what about if we have a little bit more complicated potential, like this one? So this is a parabola. That's pretty straightforward, but this is clearly not a parabola. So how would you go about this if you have a little bit more complicated potential curve? It turns out that we can work with even such potentials and do simple harmonic approximation as long as we don't deviate too much from it. And that has to do with that we can express any function f at a certain position x as a Taylor expansion. I'm going to quickly write down what that means. So the Taylor series, or series of a function f at x naught. So f can be an arbitrary function. F equals f at x naught plus 1 over 1 factorial df by dx. So the first derivative evaluated at x equals x naught, x minus x naught plus 1 over 2 factorial d squared f over dx squared evaluated at x naught, x minus x naught squared. You recognize already the pattern here, and that goes on at infinity, n equals 3 to infinity, 1 over n factorial dnf dx to the nth derivative evaluated at x naught, x minus x naught to the n. So this is basically what we've written down here. If we have a potential of the form x and we expand it at around x naught, it's u at x naught. The first differential evaluated x naught, we expand it around the minimum. So we have a minimum, we've got an extremum, and the first derivative there is 0. And then we get the higher order terms, 1 over half. And this term, if we set that as k or equivalent to k, we end up again with a simple harmonic oscillator. As long as we are close to x naught, the higher order terms become smaller and smaller and smaller. So again, a skill of a physicist is to be clear which terms to keep and which terms to drop without affecting the results too much. One example we had so far is as long as we are velocities smaller than 10% of the speed of light, we can neglect relativistic effects. Yes, we could do the full calculations, including gamma and relativistic effects, but the difference would be extremely small, and we most likely would do a mistake at some point during the calculation. Now, a good example for that is the Lennard-Jones potential. It describes the potential energy between two atoms in a molecule, so they're coupled together. The first part is repulsive, it's positive. The second part is attractive. So this part has to do with the Pauli repulsion at very, very short ranges. If you try to push the atoms together, the electron wave functions overlap and it's repulsing. The electron orbitals overlap and it's repulsive. And this is the attractive term where the molecules are attracted to long-range van der Waal attraction. You can see 10 to the 12, that falls off pretty quickly, and 10 to the 6 is a little bit more long range. And the question is, show that the motion for small displacements about the minimum is a simple harmonic oscillator and find its frequency. Now, that is mainly, once you set it up well, an algebraic exercise. So we have the potential u of x equals epsilon. That's kind of the strength of interactions, x naught over x to the 12th, sorry, that's the 12th one, minus 2 x naught over x to the 6th. And these are the terms. Now, let's expand the potential around x naught. So u of x equals u of x naught plus So we get du by dx evaluated at x equals x naught, x minus x naught, plus 1 over 2 factorial d squared u over dx squared evaluated at x equals x naught, x minus x naught squared. A quick question, does everyone know what the factorial means? Just let's take example 3 factorial is 1 times 2 times 3, 4 factorial equals 1 times 2 times 3 times 4, and so on. 1 factorial, basically I dropped the 1 factorial, here's 1 over 1 factorial, because it's just 1. Plus 1 over 3 factorial and higher order terms. If we are staying close, we can neglect the higher terms. Now, let's work our way through these 3 terms. We have got 1 here, we've got 1 here, which we need, and we've got 1 here, which we need. I'll just label that as 1, this as 2, this as 3. So we can work through them individually, and we don't, and we put them back together at the end. Otherwise, we might stumble or lose some terms. So the first one is the easiest one. U of x, u x naught equals e or epsilon x naught over x to the 12th plus, minus 2x naught over x to the 6th, evaluated at x equals x naught equals minus epsilon. Here we've got 1, 12, sorry, 1, minus 2 is minus 1, and so on. So the second term is, well, du x by dx, x equals naught. I'm focusing on those terms. This is easy, we're gonna add that at the end. Now, that term is a little bit more difficult, but we already know what to expect. We are looking at the minimum, an expansion around the minimum, so the first derivative should be 0. Unfortunately, we have to do it because we need the second derivative as well, and for that we have to work that out. So that leads to 12 epsilon minus 1 over x naught over x to the 13 plus 1 over x naught over x to the 7, and that's evaluated at x equals x naught as usual, and that is 0 as expected. Now, the last term, d squared u of x dx squared at x equals x naught equals, so we're going to continue from there, 12 e epsilon over x naught squared (13) x naught over x to the 14th minus 7 x naught over x to the 8th evaluated by at x equals x naught, and that if you collect all the terms, you end up with 72 epsilon over x naught squared. Now, these are all the terms which we've tried to solve and put together. Now, if we arrive at, or if we put them then together in the u of x, which we had originally, we end up with u of x equals, the first term we found out is minus epsilon. The du by dx is 0. And we end up then with plus 72 epsilon over x naught squared. Sorry, there's 2 factorial from which I've neglected from here. So there's a 2 factorial which I need to put in. X naught squared x minus x naught squared. So this is our potential. This is the result of the Taylor expansion. So this is the starting potential. This describes it all. We approximated it in proximity to x naught around here. And yeah, if you want, you can put a parabola on there and you see how long this is actually valid for, this approximation. And actually it's not an equal sign, it's an approximate sign because we neglected higher terms. The higher terms, the more we include, the more accurate we are. But for many parts in physics, you try to deal with small perturbation to measure things or to analyze things. Now, we have u. Now let's go to f. F of x equals minus du by dx. And that's approximately minus 1/2 times 2, and then we have the 72 epsilon over x naught squared x minus x naught equals, and then we just write that as minus k x minus x naught. This is our spring constants. So as before, and we get simple harmonic oscillator about x naught. And then from last lecture, we had omega squared equals k over m for those simple harmonic oscillators, equals 72 epsilon over m x naught squared. So we have the angular frequency of the small oscillation, so this is omega equals angular frequency. So we were able to show that the motion of small displacement, and the keyword, read every question very, very carefully. The keyword is here small displacement. And this, if that turns up in one of the questions you have to solve, try to really think hard about what that actually means when someone mentions small displacement. Here in this case, it means you can approximate it with a Taylor expansion. You're not going too far away. If a large displacement would be up here, then clearly the approximation with a parabola fails. But for small displacements left and right, you can approximate it with a simple parabola and a simple harmonic oscillator. Now, here we have to differentiate again here between two cases, bounded and unbounded potentials. For E1, we know whatever we do to this particle, it will move left and right, but it will stay bound within this potential well. The position of x are constrained, x1 between x1 and x2, because there the maximum potential energy is this one, and then it would go back and forth between those two extrema. However, if you have enough energy, then at some point we will get into an unbounded motion. So x at small is still constrained. It can't get smaller than x naught here, but at higher x, it becomes unconstrained, and we basically could kick out that particle out of this potential well. It's the same like if you want to leave Earth's gravity field, you have to have a minimum of energy to get to an unbound orbital to basically leave the potential well, and the same can be done for this Lennard-Jones potential and for many others. You have to differentiate. Do you actually kick it out? And if you start at that distance up here and let the in this potential well and let the particle relax, it's gonna shoot down, convert this potential energy to kinetic energy, and then shoot all the way out, so it will become unbound. And with that, the particle has left and is disappearing, and has at infinity, x going to infinity, still some kinetic energy. With that, today I'll probably ran a little bit through. We're finished for today, and I'll see you all next Monday again at 9 a.m. Thank you very much.